Today we are going to learn some examples on limit superior and limit inferior of a sequence. Example, find the limit superior and the limit inferior of the following sequences, and the limit inferior for the following sequences. A, sin n pi by 2, sequence sin n pi upon 2, n is equal to 1 to infinity. B, sequence 1 plus 1 by n into cos n pi, n is equal to 1 to infinity. C, sequence 1 plus 1 by n raised to n is equal to 1 to infinity. N is equal to 1 to infinity. Solution of A. Let sequence Sn n is equal to 1 to infinity. Sequence S suffix n is equal to 1 to infinity is equal to sin n pi upon 2, n is equal to 1 to infinity. This sequence can be written as Sn is equal to sin n pi upon 2 for all n belongs to I, for every positive integer n, is equal to, we write S1, S2, S3, S4, S5 and so on. Range of this sequence. Sin n is equal to 1, sin pi by 2. S2, sin 2 pi upon 2. Sin 2 pi upon 2 is that is pi. Sin 3 pi upon 2. 3 pi by 2. Sin 4 pi by 2, that is 2 pi. Sin 5 pi by 2. And so on. Sin pi by 2 is 1. Sin pi is 0. Sin 3 pi by 2. Sin 3 pi by 2 is equal to minus 1, again 0, again plus 1, and so on, and so on. Range set of the sequence Sn. Range set of sequence S suffix n is equal to 1 to infinity, is minus 1, 0, plus 1. Range set contains only 3 elements, that is minus 1, 0 and plus 1. Capital Mn, list upper bound of the set Sn plus 1, Sn plus 2 and so on is equal to, list upper bound of this set is equal to 1. Range set 1. Capital Mn is equal to 1. Limit n tends to infinity of capital Mn is equal to limit n tends to infinity of 1 is equal to 1. Therefore, sequence capital Mn, n is equal to 1 to infinity, converges to 1, converges to limit 1. Therefore, by definition, limit superior of Sn, limit n tends to infinity of superior of Sn is equal to limit n tends to infinity of capital Mn is equal to 1. Limit superior of this sequence Sn is equal to 1. Small mn, since by definition of small mn is greatest lower bound of the set Sn plus 1 and so on. GLB of the set Sn plus 1, Sn plus 2 and so on is equal to GLB of this set, range set minus 1, 0, plus 1, that is minus 1. Greatest lower bound of this set minus 1, 0, 1 is minus 1. Limit n tends to infinity of small mn is equal to limit n tends to infinity of minus 1 is equal to minus 1. Therefore, sequence small mn, n is equal to 1 to infinity, converges to minus 1. Converges to minus 1. Therefore, by definition of limit inferior of the sequence, limit n tends to infinity of inferior of Sn is equal to limit n tends to infinity of minus small mn, which is equal to minus 1. Limit superior is equal to plus 1, limit inferior is equal to minus 1. For the sequence, Sn n is equal to 1 to infinity, which is equal to sin n pi by 2. Now we see solution of B. Let sequence S suffix n is equal to 1 to infinity is equal to 1 plus 1 by n into cos of n pi. N is equal to 1 to infinity, 1 upon n. This sequence can be written as small S suffix n is equal to 1 plus 1 by n into cos of n pi. For all small n belongs to I, small n is positive integer. Now we put n is equal to 1. We find the range of this sequence. This is equal to, if we put n is equal to 1, we obtain 1 plus 1 by 1, that is 2 into cos of pi. If we put n is equal to 2, we obtain 1 plus half, that is 3 by 2 into cos 2 pi. If we put n is equal to 3, cos of, if we put n is equal to 3, 1 plus 1 by 3, that is 4 by 3 into cos of 3 pi. If we put n is equal to next integer, that is 4, we obtain 5 by 4 into cos of 4 pi. Put n is equal to 5, 1 plus 1 by 5, it gives 6 by 5 into cos of 5 pi. If we put n is equal to 6, 7 by 6 into cos of 6 pi, and so on. But we know cos even pi is equal to plus 1 and cos of odd pi is equal to minus 1. Cos pi is minus 1, it gives minus 2. Cos 2 pi plus 1, it gives 3 by 2. Cos 3 pi again minus 1, minus 4 by 3. Cos 4 pi is plus 1, 5 by 4. Minus 6 by 5, plus 7 by 6, and so on, and so on. This is sequence S suffix n. N belongs to I. N belongs to I. Here, S suffix 2n minus 1. Here, S suffix 2n minus 1. It gives S1. If we put n is equal to 1, we obtain S1. N is equal to 2, S3. N is equal to 3, S5, and so on. That is minus 2, minus 4 by 3, minus 6 by 5, and so on. In general, 2n minus 1, 2n minus 1 or 2n plus 1. If we put n is equal to 1, we must obtain minus 2n upon 2n minus 1. N is equal to 1, we obtain minus 2. N is equal to 2, minus 4 by 3, and so on, and so on. And S suffix 2n, S suffix 2n, it gives 3 by 2, 5 by 4, 7 by 6, and so on, 2n plus 1 upon 2n, and so on. In short, we write S suffix 2n minus 1 is equal to minus 2n upon 2n minus 1 for all n belongs to I. And S suffix 2n is equal to 2n plus 1 upon 2n for all n belongs to I. S suffix 2n minus 1 and S suffix 2n both are subsequences of sequences n. N is equal to 1 to infinity. The sequences, the S suffix 2n minus 1, S suffix, sequence S suffix 2n minus 1, n is equal to 1 to infinity, and S suffix 2n, n is equal to 1 to infinity, are subsequences of sequence S suffix n is equal to 1 to infinity. Now limit n tends to infinity of S suffix 2n minus 1. Limit n tends to infinity of S suffix 2n minus 1, it gives minus 1, and limit n tends to infinity of S suffix 2n, it gives plus 1. Plus 1. That is, limit n tends to infinity of S suffix, limit n tends to infinity of S suffix 2n minus 1 is equal to limit n tends to infinity of minus times 2n upon 2n minus 1 and is equal to limit n tends to infinity of minus 2n upon n upon 2n upon n minus 1 by n. is equal to limit n tends to infinity of minus 1 upon 2 upon minus 2 upon minus 2 upon 2 minus 1 by n, it gives minus 2 by 2 minus 0, which is equal to minus 1. Therefore, the subsequence S suffix to n minus 1, n is equal to 1 to infinity, converges to minus 1. To minus 1. Similarly, limit n tends to infinity of S suffix to n, limit n tends to infinity of 2n upon 2n plus 1 upon 2n is equal to limit n tends to infinity of 2n by 2n plus 1 by 2n. 1 by 2n is equal to limit n tends to infinity of 1 plus 1 by 2n is equal to 1 plus 0 is equal to 1. Therefore, the subsequence S suffix to n is equal to 1 to infinity, converges to plus 1. Therefore, we write limit superior of Sn is equal to plus 1. Limit n tends to infinity of superior of Sn is equal to plus 1. And limit n tends to infinity of inferior of Sn is equal to minus 1. Limit superior and limit inferior both exist for the sequence Sn n is equal to 1 to infinity is equal to 1 plus 1 by n into cos of n pi, n is equal to 1 to infinity. Solution of C. Let sequence Sn n is equal to 1 to infinity is equal to 1 plus 1 by n raised to n is equal to 1 to infinity. This sequence Sn can be written as Sn is equal to 1 plus 1 by n bracket raised to n for all n belongs to I. For every integer n belongs to I. Limit n tends to infinity of Sn. Limit n tends to infinity of Sn is equal to limit n tends to infinity of 1 plus 1 by n raised to n. And this is equal to E. Where 2 is less than E is less than 3. E lies between 2 and 3. Therefore, limit n tends to infinity of superior of Sn is equal to 3. And limit n tends to infinity of inferior of Sn is equal to 2. Hence the solution of C. Now we are going to learn Cauchy's sequences. Cauchy's sequences. C-A-U-C-H-Y. Cauchy's sequences. Cauchy's sequences. Definition of Cauchy's sequences. Definition of Cauchy's sequences. Let Sn n is equal to 1 to infinity be a sequence of real numbers. Then Sn n is equal to 1 to infinity is called Cauchy's sequence if for every given epsilon positive there exists positive integer capital N such that modulus of S suffix m minus S suffix n is less than epsilon for all n greater than or equal to capital N. Sequence Sn n is equal to 1 to infinity is called Cauchy's sequence if for every epsilon greater than 0 there exists positive integer capital N such that modulus of Sm minus Sn is less than epsilon for all n greater than or equal to capital N. Let sequence Sn n is equal to 1 to infinity be a sequence of real numbers. Then sequence Sn n is equal to 1 to infinity. Then sequence Sn sequence S suffix n is equal to 1 to infinity is called a Cauchy's sequence. Cauchy's sequence if for every epsilon greater than 0 there exists positive integer capital N or capital N belongs to I. Capital N belongs to I. Such that modulus of S suffix m minus S suffix n is less than epsilon for all n greater than or equal to capital N. For all small n greater than or equal to capital N. This condition can be written as modulus of S suffix n minus S suffix m is less than epsilon for all n greater than or equal to capital N. Capital N. Theorem number 1. Theorem number 1. Statement of theorem number 1. If the sequence of real numbers if the sequence of real numbers Sn n is equal to 1 to infinity converges then sequence Sn S suffix n is equal to 1 to infinity is a Cauchy's sequence. Cauchy's sequence. Sn n is equal to 1 to infinity is convergent sequence of real number. Then Sn n is equal to 1 to infinity is a Cauchy sequence. Then we have to prove that Sn n is equal to 1 to infinity is a Cauchy sequence of real number. Proof of this theorem 1. Since by hypothesis the sequence of real numbers Sn n is equal to 1 to infinity S suffix n is equal to 1 to infinity converges to L say. Therefore, by definition of convergent sequence, limit n tends to infinity of Sn is equal to L. By definition of convergent sequence, by definition of convergent sequence, limit n tends to infinity of Sn is equal to L. L is limit of this sequence Sn. By definition of limit of sequence, by definition of limit of sequence, for every given epsilon positive, epsilon by 2 is also positive. For every epsilon positive, epsilon upon 2 positive. We take epsilon is equal to epsilon by 2 positive. There exists positive integer capital N such that modulus of Sm minus modulus of S suffix n minus L less than epsilon. Epsilon is epsilon by 2. Less than epsilon for all small n greater than or equal to capital N. Epsilon positive, epsilon upon 2 positive. By definition of limit of sequence, for every epsilon by 2 positive, there exists positive integer n belongs to I such that modulus of Sn minus L is less than epsilon by 2 for all n greater than or equal to capital N. If we put n is equal to m, we obtain modulus of Sm minus L less than epsilon by 2 for all small m greater than or equal to capital N. Replacing small n by m, we obtain S suffix m minus L is less than epsilon by 2 for all m greater than or equal to capital N. This is say 1. This is say 2. Now, modulus of, we write here for n is equal to m, we obtain Sm minus L is less than epsilon by 2 for all m greater than or equal to capital N. Now, modulus of Sm minus Sn is equal to modulus of S suffix m minus L plus L minus Sn. We have added L and minus L. Modulus of A plus B less than or equal to mod A plus mod B. Therefore, this is less than or equal to mod of Sm minus L plus modulus of L minus Sn. S suffix n. LHS mod of Sm minus Sn is less than or equal to mod of S suffix m minus L, first modulus, plus plus modulus of minus into bracket Sn minus L. Taking minus sign as common, we write minus into bracket Sn minus L. And this term can be written as mod of AB is equal to mod A into mod B, that is mod of minus 1 into mod of Sn minus L. Therefore, LHS S suffix m minus S suffix n is less than or equal to Sm minus L plus mod of minus 1 into mod of Sn minus L. Again, mod minus 1 is equal to plus 1. Therefore, we obtain modulus of Sm minus Sn is less equals modulus of Sm minus L plus mod of Sn minus L. From 1 and 2, each modulus on RHS is less than epsilon by 2 plus epsilon by 2. For all m, n both are greater than or equal to capital N. Therefore, this RHS is strictly less than epsilon by 2 plus epsilon by 2 for all m, n greater than or equal to m, n greater than or equal to capital N. By 1 and 2. By using 1 and 2. Therefore, LHS mod of Sm minus Sn is strictly less than epsilon plus epsilon by 2 plus epsilon by 2 becomes epsilon. For all small m, n greater than or equal to capital N. Small m, n greater than or equal to capital N. Therefore, by definition of Cauchy sequence, by definition of Cauchy sequence S suffix n is equal to 1 to infinity is a Cauchy's sequence. Hence the proof of theorem number 1. Hence the proof of theorem 1. Theorem 1. Now we prove the lemma. If Sn is equal to 1 to infinity is a Cauchy sequence of real number. If sequence Sn is equal to 1 to infinity is a Cauchy sequence, Cauchy, Cauchy sequence of real numbers. Cauchy sequence of real numbers, then Sn is equal to 1 to infinity is bounded. S suffix n is equal to 1 to infinity is bounded. Sn is equal to 1 to infinity is a Cauchy sequence of real numbers. Then we have to show that Sn is equal to 1 to infinity is bounded. Sn is equal to 1 to infinity is bounded sequence of real numbers. Proof of this lemma, since my hypothesis sequence Sn n is equal to 1 to infinity is a Cauchy sequence of real number. Cauchy's sequence of real numbers. Therefore, by definition of Cauchy's sequence, by definition of Cauchy's sequence, for every epsilon is equal to 1 greater than 0, there exists positive integer capital N which belongs to I, capital N, positive integer capital N, or N belongs to I, such that modulus of S suffix M minus S suffix N is less than 1 for all M N greater than or equal to capital N. Capital N is positive integer. Positive integer. This is say 1. In particular, if small n is equal to capital N. In particular, if this small n is equal to capital N. In particular, small n is equal to capital N, we obtain modulus of S suffix M minus S suffix capital N is less than 1 for all small m greater than or equal to capital N. And this is a relation 1, relation number 1. Now, mod of Sm, mod of S suffix M is equal to modulus of S suffix M minus S suffix capital N plus S suffix capital N minus Sn and plus S suffix N, it becomes 0. This is less than or equal to, by properties of modulus, mod of A plus B less than or equal to mod A plus mod B. Modulus of S suffix M minus S suffix capital N plus mod of S suffix capital N. By 1, S suffix M minus S suffix N is strictly less than 1. Therefore, we write mod Sm, mod S suffix M is less than or equal to modulus of S suffix M minus S suffix capital N plus mod of Sn, and this is strictly less than 1 plus modulus of Sn by using 1. This is strictly less than 1 plus mod Sn, mod S suffix N, for all small m greater than or equal to capital N by using 1 or by 1. That is, mod S suffix M is strictly less than 1 plus mod Sn for all m is equal to capital N. M is equal to capital M, M is equal to capital N, M is equal to next integer capital N plus 1, M is equal to capital N plus 2, and so on. That is mod S suffix M is less than 1 plus mod Sn for all small m greater than or equal to capital M. This is a relation to. Let capital M is equal to maximum of modulus of S1. We write in curly bracket mod S1, mod S2, mod S3 and so on up to mod of S suffix capital N minus 1. We take capital M is the real number which is maximum of modulus of S1, modulus of S2, modulus of S3, modulus of S suffix capital M minus 1. It means that capital M is greater than or equal to S1. Capital M is greater than or equal to S2, mod S2. Capital M is greater than or equal to mod S3 and so on. Capital M is greater than or equal to mod of S suffix N minus 1. In short, we write modulus of S suffix R is less than or equal to capital M for all R is equal to 1, 2, 3 and so on capital N minus 1. In short, we write mod of S suffix R is less equals capital M for all R is equal to 1, 2, 3 and so on capital N minus 1. This is say 3. From 2 and 3 we write from 2 and 3 we write modulus of S suffix M. Modulus of S suffix M is less than 1 plus capital M plus mod Sn, nth term of the sequence. For all M belongs to I means for all M is equal to 1, 2, 3 and so on up to infinity. Therefore, the sequence S suffix M is equal to 1 to infinity is bounded sequence of real numbers. Therefore, by definition of bounded sequence, bounded sequences of real numbers. Sequence S suffix M is equal to 1 to infinity is bounded sequence of real numbers. Hence we write sequence Sn is equal to 1 to infinity is bounded sequence of real number. Hence we write sequence Sn is equal to 1 to infinity is bounded sequence of real numbers. Sequence of real numbers. Since range of this sequence is S1, S2, S3, Sn and so on, and range of this sequence Sm M is equal to 1 to infinity is S1, S2, S3 and so on. Range set is same. Therefore, sequence Sn is equal to 1 to infinity is bounded sequence of real number. Hence, the proof of lemma. Thank you for watching the video.